continue with first equation.
Okay, so my topic today is quadratic forms. So let me just begin by reminding you that an n-dimensional quadratic form is a homogeneous quadratic polynomial in n variables. So quadratic forms appear in many different contexts, in pure and applied mathematics, and even theoretical physics. For example, the Lorentz metric in special relativity is a quadratic form. So the modern-day study of quadratic forms falls into two rather distinct areas, algebraic and analytic. And my subject today is purely on the algebraic side. So here is a very brief and very subjective history of the algebraic theory of quadratic forms. So it goes back to the mid-19th century, to Sylvester's law of inertia, which I will discuss later in the talk. Sylvester classified quadratic forms over R. So this is now an important part of linear algebra. So in 1937, Witt introduces what we now call the Witt ring, which I'll also define later in the talk, and proves his fundamental theorem about the structure of quadratic forms over arbitrary fields of characteristic different from 2. So in the 1960s, Pfister introduces a special class of forms, which he called multiplicative forms, and are now called Pfister forms. These are the basic building blocks of the Witt ring. After that, in the 1970s, there was a lot of activity in this area by purely algebraic techniques. The whole theory is very appealing. It's very elementary. I heard that in Germany, at one point, it was even included into the undergraduate curriculum. So at that point, John Milner, so a great topologist, became interested in the subject and introduced what's now called Milner's K-theory, and stated his famous conjectures that guided the development of the subject for the next 30 years or so. In the early 80s, Merkurjev proved Milner's conjecture in dimension 2. That was a huge breakthrough. And the Merkurjev-Suslin theorem followed soon after that. In the mid-90s, Voevodsky, the student of Suslin, proved Milner's conjecture in all dimensions. He was awarded the Fields Medal for this achievement in 2002. So that was the beginning of the present period. So we're very far away from the kinds of techniques, purely algebraic techniques, that were used in the 1970s. So the modern day techniques involve motives and Chow groups. And so these techniques led to solutions of a number of outstanding open problems that weren't that didn't yield to the more elementary algebraic techniques. And so the book, The Algebraic and Geometric Theory of Quadratic Forms by Elman, Karpenko, and Merkurjev, popularizes these developments, and that's where we are today. So today's lecture will lean more heavily on the classical aspects of the theory. So I will be quite informal and elementary, at least at the beginning. And my final goal is is a theorem on the Pfister number of a quadratic form, which I proved jointly with Patrick Brosnan and Angela Vistoli in 2010. So, so let me start with the basic setup. So this is what I mean by a quadratic form. It's a polynomial of degree 2 in n variables. The field can be arbitrary. The base field can be arbitrary of characteristic different from 2. The coefficients a, I, j are symmetric, and they're taken, these are of course x1 through xn, they're commuting variables, and they're taken to be scalars in f. So to such a quadratic form, we can associate a symmetric matrix called the Gram matrix. And we can associate to it a symmetric bilinear form, which is very closely linked to the quadratic form. So Q of V is just B of VV. And so one can recover from the bilinear form, one can recover the quadratic form. From the quadratic form, one can recover uniquely the bilinear form in this way. So this is all one learns over the real numbers. One learns of this in the linear algebra class. In characteristic 2, of course, that 1/2 becomes a problem, and the link between quadratic forms and bilinear forms is not quite as direct in that setup. So of course, what makes all of this interesting is that we identify quadratic forms. We say that they're equivalent or isomorphic if one can be transformed to the other by a change of basis in our underlying vector space. And the same for symmetric bilinear forms. So it's very easy to see that the following objects are in a natural bijective correspondence. So I've already talked about quadratic forms and symmetric bilinear forms being recoverable from each other. And so if we associate to a quadratic form its Gram matrix, then two forms are equivalent if and only if their Gram matrices are related by this formula here for some non-singular n by n matrix A, which is the change of coordinates matrix. So quadratic form is non-degenerate if its Gram matrix is non-singular. And we will mostly concentrate on non-degenerate forms in this talk. So if I don't say anything, I'm probably assuming that the form is non-degenerate. Okay, so the Gram-Schmidt process allows one to diagonalize a quadratic form. So that means that the Gram matrix becomes diagonal. In other words, the quadratic form, any quadratic form, Q is equivalent to one of this form, sum of squares with some coefficients. So the usual proof from linear algebra assumes that the field is R, and then Q is positive definite. I'm not assuming any of that. In fact, F, it's not even clear what positive means for an element of F in general. However, the proof goes through with only minor changes. So just to remind you how the proof goes, we choose some vector x, say v, and then take the orthogonal complement to v, and then you do this inductively. So if the form is positive definite, then this v will have a Q of v will be non-zero, and the orthogonal complement will never intersect the line that is spanned by v. So we can continue inductively. It's very easy. In general, it is possible that Q of v is 0. We're not ruling that out. Such a vector is called isotropic. So we have to choose this v a little bit more carefully, and then everything will work out. The orthogonal complement will again be disjoint from the line spanned by v, and we can continue inductively. So this can always be done. as long as the characteristic is not 2, which I will assume throughout. So the notational convention is that this form here is denoted like that. So Q is non-degenerate simply means that all the coefficients are non-zero. And again, we are only interested in these forms up to equivalence. So in particular, if we permute the AIs or modify any of them by a square in F, that will give us an equivalent form. So natural question, naive natural question is under what conditions are these forms equivalent? So recall, again, since I can't keep my notation on the board, I'm just reminding you what it means here. So this seemingly innocent question is surprisingly deep. So Milner's conjecture only gives a very partial answer to it, and even led to some of the deepest mathematics that exists now. So I will discuss Milner's conjecture later in the talk, but I guess the short answer is that it's not known. It is a very simple and innocent question, but there is no simple answer to it. It depends very much on the field F. So if we have two forms, we can add them together and we can form tensor products. So those are new quadratic forms on either the direct sum or the direct product of the two underlying vector spaces. And if our forms, so the bilinear form is simply given in this way, associated to the tensor product. So in very concrete terms, if we've already diagonalized our forms, then the direct sum is just obtained by appending one form to the other, and the tensor product it's like the tensor product, the Kronecker product of diagonal matrices. So we take all possible products. But this is deceptive because, we couldn't have defined for the tensor product, for example, in this way. Because to define it in this way, we would have to prove that if I replace, say, Q1 by an equivalent form, then what comes out here is equivalent. So I need a formula like this, a coordinate-free formula, to actually show that it's well defined. And only then I can write down something like this. So these two operations, direct product and tensor product, define a semi-ring structure on the set of equivalence classes of quadratic forms. I will temporarily denote the semi-ring by S of F. So the zero element here is the zero-dimensional form on the zero-dimensional vector space, and the multiplicative identity is the one-dimensional form, f of x equals x squared. So the reason that my notation here is temporary, and I will not really use it again, is because this structure is not very useful. There's no additive inverse here. I guess this is obvious, but I'll say it anyway. There's no additive inverse because the dimensions add. So if I have a form Q that's of some positive dimension n, if I add another form to it, the dimension will only increase. So I will never get the zero form like this. So Ernst Witt had the brilliant idea how to define a ring structure in this set of quadratic forms by using a slightly weaker notion of equivalence. So this notion is now what's now called width equivalence. And so as I said before, if Q of V is 0 and V is a non-zero vector, we say that this vector is isotropic. And the form itself, if it admits an isotropic vector, is called an isotropic quadratic form. So the two-dimensional isotropic quadratic form, f of xy equals x squared minus y squared, is called the hyperbolic plane. And it plays a special role in width theory. It is easy to see, and I will use this later, that H is the unique non-singular isotropic two-dimensional quadratic form. So in particular, this kind of form so f of xy equals ax squared minus ay squared is also two-dimensional and isotropic. Obviously isotropic, because if I plug in 1, 1, I get 0. So for any non-zero a, this is isomorphic to H. It's not difficult to see, to find the linear transformation of the two-dimensional space that takes one to the other. They're both isomorphic to f of xy equals x times y. But this is a useful observation. So quadratic form that's isomorphic to a direct sum of hyperbolic planes is called hyperbolic. So such a form can only exist in even dimensions, right? Because I'm adding some two-dimensional forms. So two forms are called width equivalent. Again, these are non-degenerate quadratic forms if they differ by hyperbolic form. In other words, if Q plus some number of hyperbolic forms is isomorphic to Q prime plus a certain number of hyperbolic forms. A priori, Q and Q prime may be of different dimensions. You see, once you increase the dimension, there's more room for equivalence. There are more linear transformations there that can take one to the other. So an easy lemma is that Q is isotropic if and only if one can split off a hyperbolic plane. If and only if Q is Q prime plus a two-dimensional form for some form Q prime of dimension 2 less than the dimension of Q. So applying this recursively, we can obtain a decomposition Q of Q as a direct sum of an anisotropic form plus some number of hyperbolic forms. And which showed that this anisotropic form is uniquely defined. It doesn't matter how we split off these hyperbolic planes. So in other words, every non-degenerate quadratic form is width equivalent to a unique anisotropic form QA. So the width ring is now defined as a set. The underlying set consists of non-degenerate quadratic forms defined over F up to width equivalence. So the operations are the same ones I defined before, direct sum and tensor product. These are well defined on width classes because H tensor Q is hyperbolic. That's very easy to see using this formula. And I wrote this out. So if I take the tensor product of Q, which I denote by A1, so in diagonal, the diagonalization of it is A1 through AN, and I tensor it with a hyperbolic form, I get this sum, and each summand is hyperbolic. Oops. So each summand is isotropic and two-dimensional, and therefore is a hyperbolic plane. So the zero element is the zero-dimensional form, and the multiplicative identity is the width class of the one-dimensional form 1. And so now we are really dealing with a ring because each quadratic form has an additive inverse. And again, there's an obvious formula here that expresses the additive inverse. So we lose something in the process because the dimension of a width class, an element of the width ring, is not well defined. It's only defined modulo 2 because we can add hyperbolic forms. So mod 2, that doesn't change the dimension. So we have this homomorphism from the width ring to the integers mod 2. It's a ring homomorphism, and its kernel is what's called the fundamental ideal in WF. It consists of even-dimensional forms. So for example, if F is quadratically closed, then this, of course, these fields are trivial, where F that are closed under taking square roots. From the point of view of quadratic form theory, these are as good as algebraically closed, and so they don't admit any non-trivial forms. So in this case, this homomorphism is an isomorphism. But that's really not the kind of field we're interested in. And conversely, if this isomorphism, if this homomorphism and this is an isomorphism, then the field is quadratically closed. Okay, so now we come to Sylvester's law of inertia, which is a theorem in linear algebra. So every quadratic form can be diagonalized, and then some of the coefficients are positive and some are negative. And we can rescale by the square root of the absolute value to get a bunch of ones and a bunch of minus ones. And so up to equivalence, Q is uniquely determined by R and S. So R is the dimension, the biggest dimension of a subspace where the form is positive definite. Sylvester introduced the difference between the two of them, R minus S, that's called the signature. And if you're looking at this form up to width equivalence, we're allowed to remove 1 and minus 1 together because those two form hyperbolic plane. So R and S individually can vary within the same width class, but the difference between them, the signature, remains constant. So Sylvester's theorem in modern terms can be written as follows. The width ring of the real numbers, the homomorphism that is given by taking a quadratic form to its signature is an isomorphism of rings. So in this case, the fundamental ideal consists of even-dimensional forms, and those correspond to even signatures. So in this case, the width ring is very simple, but of course, the real numbers are very close to being too closed. Right, so that's not the kind of field we want to work with either. Okay, so for more complicated fields, the width ring is a very delicate invariant of F. So the most natural way to extract information from it is to use the fact that it's a local ring where the fundamental ideal is a maximal ideal. So one can look at various powers of this maximal ideal. So the powers consist of width classes of direct sums of forms like that are tensor products, where each qi is a two-dimensional form. So that's just the definition of a power of an ideal. So loosely speaking, I1, I2, and I1 and I2 are well understood. I3 is sort of in the middle. And then after that, they are poorly understood. So for example, let me describe I2. So remember, I itself is the kernel of the dimension homomorphism. So these are forms of even dimension. So I2 is the kernel of the determinant or discriminant. So let me just assume that -1 is a square in F. So this is a recurring problem in quadratic form theory, that everything can be done without this assumption, but one has to worry about powers of -1, and I don't want to spend too much time on that. So, so -1 is a square. In particular, any entry that I have that is minus a, I can replace by plus a, because I can rescale by a square. And -1 is a square. So in particular, the determinant of the hyperbolic form is the product of 1 and -1. So it's -1, and it is a square. So the determinant is just the determinant of the Gram matrix. And the Gram matrix G can be replaced by an equivalent one, which is A, G, A transpose. So that's only defined up to squares. So the determinant takes values in F star mod F star squared. And so the theorem, fairly easy one, is that I2 is the kernel of the determinant homomorphism. In other words, I2 consists of width classes of even dimensional forms of determinant or discriminant 1. So the difference, again, between the determinant and the discriminant is some power of -1 that I want to avoid by declaring -1 to be a square, just for expositional purposes. So let me now tell you what the Pfister form is. So, so these are basic building blocks of the width ring. And they're just, so one-fold Pfister form is a one-dimensional form of the form 1, comma A. And then the two-fold Pfister form is a tensor product of two of these. So it's 1, A1, A2, comma A1, A2. And the three-fold Pfister form is a tensor product of three of those. And the k-fold Pfister form is this kind of form, and it has dimension 2 to the k. And it lies in the kth power of the fundamental ideal by definition. So a very simple lemma is that every form in the kth power of the fundamental ideal is equivalent to a sum of k-fold Pfister forms. So by definition, such a form Q is a direct sum of k-fold tensor products, where each Qi is even dimensional, but then we can break each Qi as a direct sum of two-dimensional forms. So since we're assuming that -1 is a square, we can write each Qi, say Qi is Si Ti, then we can write it as a direct sum of two-dimensional forms that are Pfister forms. Right? Because the 1, 1 is trivial, is hyperbolic. And so we can, using this decomposition, we can rewrite this product as a sum of Pfister forms. Okay, so the minimal number of k-fold Pfister forms that are required to represent an element of the kth in the kth power of the fundamental ideal is called the kth Pfister number of Q. So this number depends on both k and f. So the question I want to address is, what is the biggest Pfister number as q ranges over all? So I fix the dimension of q, and I fix k, but I allow f to range over all fields, and I allow q to range over all forms in this kth power of the fundamental ideal. So let me just say a few words about the first and second Pfister numbers. They're quite easy to compute. So the first Pfister number is at most n, and the second Pfister number is at most n minus 2. So let me show you how to, so you get a feel for this. So again, I'm assuming that minus 1 is a square. So if I have an n-dimensional form, so n is even here because I'm assuming that q is an I1. Right? So I write this form as 1a1 plus 1a2, etc. And each one of those is a one-fold Pfister form, each summoned here. So I need n to do this. Okay, so that's the proof of part A. And for part B, there's a trick like this, but a little bit more complicated, only a little bit. So if you decompose this first form, it's 1, A1, A2, A1, A2. So the A1, A2 is going to cancel this A1, A2, and the 1 is going to cancel this 1. So here I'm assuming that this form has discriminant 1, so I can assume that the product of these is 1, and it's even dimensional. That's what I mean by saying that q is an I2. So this is a simple formula that gives me my original form, writes it as a sum of n minus 2, two-fold Pfister forms. So Parimalis, Suresh, and Tignol showed that both inequalities in the lemma are in fact sharp, that one can't, in general, one can't represent these forms as sums of Pfister forms with fewer summons. So informally speaking, the complexity, so I'm thinking these Pfister forms as basic building blocks. So the complexity here only increases linearly with the dimension. So now I want to know if something like this works for higher powers of the maximal ideal. So in particular, is there always an upper bound depending on the field k? Sorry, depending on the power k and the dimension n, such that the Pfister form, the Pfister number of every q which lies in the kth power of the fundamental ideal is bounded by this number. And if such a number exists, then moreover, we always choose it to be linear in n? And the answer to the first question is yes, for k at most 3, and unknown for k greater than or equal to 4. So the main result I want to present today implies that the answer to the second question is no, for k equals 3. So there is an upper bound like this, fk of n, but it is exponential in n. It's not linear in n. Okay, so let me talk a bit about the Milnor conjectures because they're relevant here. So Milnor's conjecture says that Okay, so remember, the original idea was to understand the Witt ring. The Witt ring has this fundamental ideal, so it's natural to look at the powers of the fundamental ideal. So the Milner's conjecture says that if we take the kth power and mod out by the k plus first power, we get a vector space that's isomorphic to the kth cohomology of F with coefficients in Z mod 2Z. It's mod 2 coefficients. So it doesn't really answer the question about the structure of the Witt ring itself, but it's sort of the graded version of it. And there's a third object. So the Milner's conjectures actually concern isomorphisms among three different objects. So one is this a graded Witt ring. The other one is cohomology, Galois cohomology with mod 2 coefficients, and the third one is Milner K-theory. But I'm going to leave that out. So I'm only going to be concerned with the Witt ring in this talk. Pardon me? For every k, yes. Yeah, sorry. Yeah, n and k are the same. So, so this conjecture was proved by Watsky in the late 1990s. So I've already mentioned the Fields medal. So one thing I want to point out is that this cohomology so there's some special elements here. So if one takes elements in H1 and takes cup products, so if A1 through AK are elements of H1, then one can form these special elements. They're called decomposable elements. So maybe I shouldn't use K. Or maybe I should. Sorry. So these are in non-zero elements of F. And so AI is then an element of H1 of F Z mod 2, which is just F star mod F star squared. So now I can take cup products and these elements of this form these are called decomposable. So under the Milner isomorphism, they correspond to Pfister forms. So these correspond to a 1A1 tensor 1 AK in IK of F mod I K plus 1 of F. That was, yes. So the question I'm asking about the Pfister number, if one looks at that modulo, let me see if I have something on that here. If one looks at this quadratic form, modulo, so my quadratic form is an IK. If one looks at it modulo the next power, then what I'm asking is related to the number that's called symbol length. You know, how many of these decomposable classes are required. And that is, so modulo this, almost nothing is known about this question in the wit ring, but if one looks at it in cohomology, modulo the next power, then even less is known. I think I have something on that on the next slide. Let me just point out to you that this dimension mod 2 is the first Milnor mod, A0. So the 0th power of the fundamental ideal is the wit ring itself. Modulo the first power is isomorphic to H0, which is just the integers mod 2. So E0 is my dimension map, and E1 is the determinant map. So the determinant takes us to F star mod F star squared, which is H1. Okay, I guess I did say it on the slides. So this just repeats what I said here. So EK, so in these cases and in general, EK takes Pfister forms to pure symbols or to decomposable classes. And in that way, the kth Pfister number is analogous to symbol length in cohomology. It's the minimal number of these decomposable or pure symbols required to represent a given class. And of course, we want to take a general class, the most general class that would require the highest number, and to know what that highest number may be. So symbol length is poorly understood, and to give you an example of how poorly it is understood, even for k equals 2. For k equals 2, I had a very simple bound before of n minus 2, where n was the dimension. But here, it's called the Merkurjev-Suslin number. So if you have a central simple algebra, say of index a power of 2, then the Merkurjev-Suslin theorem tells us that it is Brouwer equivalent to a product of cyclic algebras. And the question is, how many cyclic algebras do we need to take? So the cyclic algebras correspond to these symbols AI times AJ. Sorry, A times B, just the two of them, because we are in H2. And even there, this number, this is completely unknown. Okay, so here's the main theorem, which came as a surprise, at least to us, in view of these earlier results. So for every n starting from 2, so here n really is the dimension. So k, what I denoted k before, is now denoted by 3. So here, from now on, k equals 3, right? So there is a field, and there is an n-dimensional form such that it cannot be written as a sum in the wit ring of fewer than this exponential number of Pfister forms. So informally speaking, the complexity of a form in I3 increases exponentially with the dimension. Okay, so now I want to give a few remarks on the proof. I'm not going to give any of the details, but just to give you the flavor of how we do it. So the first 3 powers are special, as I said before, because they're related to algebraic groups. So finally, I'm at the end of my second talk, and finally algebraic groups come up. So the first one, I1, is related to the orthogonal group, or torsors for the orthogonal group over the field F. The second one is related to the special orthogonal group, which probably wouldn't surprise you given that those correspond to determinant 1 forms, right? Even dimensional determinant 1. And the third one are related to the spinor group. And I'm, just for the experts, I'm going to fudge the difference between spin and G spin. But it's not going to make, for my exponential bounds, it's not going to make a difference. It's the most it's going to make is a difference of 1. So the proof relies on the following lemma, which is a consequence of our earlier work on the essential dimension of spin groups. So there exists a field F containing C in the quadratic form Q over F with the following property. Let's say that Q descends to some subfield F naught of F. So where F naught is an intermediate field between the complex numbers and F. And most importantly, Q naught is also in I3. Then, because if Q naught were not required to be in I3, I could just diagonalize, and I could just take F naught to be the field that's generated by the diagonal entries, and there would be at most n of them. So F naught would be a very small field. But if I require Q naught to also be in I3, then the transcendence degree of this F naught is bounded from below by an exponential function of n. So this is the key ingredient. And let me just explain how this ingredient is relevant here. So let's say I can write Q as a sum of a certain number m of threefold Pfister forms. Let's say a small number. So then Q descends to this field F naught, which is generated by all the coefficients. So there will be 3m coefficients. And over this F naught, each of these Pfister forms is still in I3 by definition. So I found my Q naught on the right-hand side that's defined over this small field. So therefore 3m has to be greater than or equal to this number, 2 to the power n over 2, and therefore m should be greater than or equal to 2 to the power n over 2 over 3. So this is not quite correct. I mean, this is the spirit of the argument. It's not quite correct, and it is considerably stronger than what I'm claiming in the theorem. So what is the problem with this argument? So the problem is that this equality here between Q and the right-hand side is actually width equivalent. It's not isomorphism. And the theorem, if you look at the theorem here, or what I call the lemma, is, so here I have to have equality, not just width equivalence. Okay, so we know, in other words, just to rephrase the problem, we know that Q cannot descend to a subfield of small transcendence degree, but it's conceivable that if I add some hyperbolic forms, it might. So another way to sum up this difficulty is that the relationship between this torsor, the spin n torsor, and associated to Q, and the spin n plus 2 torsor associated to Q plus H is not so clear. Is not transparent at the level of, so width equivalence doesn't translate very easily into the world of torsors. So our proof overcomes this difficulty, but only at the expense of getting a much weaker bound, but still exponential. So let me just conclude by saying a few words about higher powers of the maximal ideal. So our proof is based in a key way on these groups and the connection with torsors. And that breaks down for higher k. So for higher powers of k, almost nothing is known. But it is quite conceivable that there is no maximum. So that the Pfister number within I4 can simply be unbounded, depending on how one takes, which form one takes. for k up to 3, there is always a versal form that comes from the versal torsor, from some versal. I mean, it's not unique, it's not universal, it's only versal. But if one takes a versal torsor for these groups and takes the associated quadratic form, it gives the maximal Pfister number. So there is a bound that doesn't depend on the form. But there's no such form for k starting from 4. So it is not quite clear what to do there. So let me stop.
Any questions? How crucial is it working with fields that contain C? I mean, that's not.
Not at all, no. I mean, in the paper, characteristic 2 is different. But I just working with C to indicate that there are additional difficulties if you want to do this over a non-algebraically closed field. So these bounds become the lower bounds become even stronger. One needs even more Pfister forms, and the essential dimension can only get bigger. So I'm just doing this in this lecture and the previous one to indicate that these bounds are geometric in nature, kind of making it more difficult for myself, not the other way around.
Do you anticipate any combinatorial way of calculating these Pfister numbers here for specific fields?
You mean for I3?
For example, yes. I mean, at the end of it just gives the impression that it's sort of, maybe I'm comparing this to number, but you ask for a minimal number of generators that are needed to get the
Yeah, so the explicit formulas for k equals 1 and 2 are so simple that, I mean, this is what makes this this lower bound surprising. So I don't think it was expected.
So the Hasse-Wittig invariant for I3 is 0?
Yes. So I3, so the Hasse-Wittig invariant is the third Milnor functor.
So that will be
Right,
zero.
so
That's why you get it rather than
yeah, Milnor's conjecture says precisely that there is there's this invariant from IK F, so that's the kth power of the fundamental ideal, to HK so that the kernel is IK plus 1. And so the E0 is dimension mod 2, E1 is the discriminant, and E2 is the Hasse-Wittig invariant. And the kernel is exactly I3. Yeah, so the torsors for G spin are exactly these forms. For torsors for spin have a little bit more information that can throw off my bounds by at most 1. So that's already taken into account in the statement of the theorem, but for the slides I kind of disregarded that difference between the two of them.